Welcome to Lecture 12 of Topology at last. Sorry for the delay on these guys. So let's begin with a definition of what is a connected component. So let X be a topological space. The subspace C of X is called a connected component if, number one, C is connected, and number two, it's kind of the largest connected subset which contains C. So if you have another connected subset which contains C, it must actually be C itself. All right, so these are sort of maximally as big as you can get connected components. I'm using the word to define the word, sorry, but it's just a natural term. So you connect as much as you can of a particular topological space and put it all together, you got a connected component. Now, of course, if there's just one connected component, then that would mean that the space is just connected, right? But not all topological spaces are connected. So there are usually interesting things to say about the connected components of a topological space, so let's kind of go on here. Example 1. All right, so here it is. Suppose C is an open and closed, connected, and non-empty subset of the topological space X. Then C is a connected component of X. All right, so to see that that's a claim, right? So suppose A is connected and it contains C, all right? But C is open, all right, and it's closed, which means that A equals C, since the connected set A has no open and closed subsets except for itself and the empty set. So there you go. So if you have a subset of a topological space which is both open and closed and connected, it's a connected component. All right. So that's kind of nice, because testing maximality might be kind of tricky, but proving something's both open and closed, we've got various tools in our toolbox to do that. All right. So let's go on here. Lemma. Okay, let me zoom in just a wee bit here. All right, lemma. Let Y be a connected subspace of X, and let Y be contained by W, and W be contained by the closure of Y. Then it follows that W is connected. Moreover, the closure of a connected subspace is connected. All right, well, okay. Let Z, a subset of W, be non-empty, and suppose Z is both open and closed in W. All right. Observe Z intersect Y is open and closed in Y because of the subspace topology's definition, right? And since Y is dense in Z because of this condition right here, well, let's see here. I'm trying to prove that W is connected right now. So what I'm doing at the moment is I'm taking a subset of W which is both open and closed. My goal at the moment is to show that Z is equal to W, right? Because if I can do that, then that proves that W is connected. Let's see here. Well, anyway, going on here. So Z intersect Y is open and closed, all right, in Y by the subspace topology. And since Y is dense in Z, why is Y dense in Z? I guess because it's contained in, I guess it's because Z is contained in the closure of Y, I guess. And Z is open in W. We have that Z meets Y somewhere, but Y is connected, so Y is a subset of Z. All right. All right, and then but as y is dense in z, it's closed in w, which means z is equal to w. All right. Sorry guys, it's been a few days since I wrote these, and I feel like I'm missing something here, but my apologies, we must go on. All right, so anyway, just to reiterate here, if you have a connected subspace and you've got another set which is between that set and its closure, then it follows that that subset must be connected. I guess I think part of what's bugging me is, like, I'm trying to impose a converse of example 1 here. Like, example 1 is saying, suppose you have an open, closed, and connected. Open, closed, connected, non-empty, and then that implies that it's a connected component, right? But it doesn't, I don't think it has to be the case that every connected component is both open and closed in the superspace in which it lives. I don't think. Otherwise you just have y is equal to y closure. If y was connected implies that y is closed, then you'd have y equals to y closure, and this lemma, it seems, could be replaced with something less subtle. So I think what's messing with my mind is I'm trying to impose a converse to example 1, which is not true. So anyway, let's go on here. My apologies for the yard work, if you can hear it. If you can't, well, good. All right, so lemma number 2. Here we have, and trying to keep my. All right, so let x naught be an element of a topological space, and take a family of connected subspaces in X, each of which contains x naught. All right. Then, as long as you've got all of these subspaces meeting at that point, it follows that their union is connected. All right. So if we suppose towards we had this theorem before. We had this theorem before for path-connected spaces, right? It was pretty easy to prove for path-connected spaces, at least for two path-connected spaces. If their intersection's non-empty, you just, basically you join 2 points in the set by just taking a path which, goes through the point where they meet. So this here is, now this isn't path-connected, right? These are just connected subspaces. So this is kind of a little bit different. Like, we can't use paths here because we don't necessarily have path connected, okay? And anyway, so it supports towards the contradiction that you've got W is, and I guess we'll just do it for 2. W is equal to A union B, where A and B are non-empty, and they're non-empty open with A intersect B equal to empty set. Wait a minute, wouldn't I? I'm sorry. So I'm supposing W, I'm still imposing W is equal to what it is up here, and I'm not doing it for 2. I'm still doing it for, a family of connected subspaces, but I am now supposing that family of subspaces W is not connected, which is to say that there's a separation, which is, I'm assuming, right here, right? So yeah, non-empty open sets that are disjoint and yet whose union forms W. So without loss of generality, suppose x naught is an element of A, all right? Because x naught's got to be in one or the other, because x naught's definitely in W, since it's in every single one of these z sub i's. It would suffice for x naught to be even in one of those, since we're forming a union. Okay, so sorry, I'm sipping my tea. So x naught's an element of A without loss of generality. It's either got to be in A or B, so let's just say A. And it could be in both, but let's suppose it's in A. So x naught's in A, then we know that A intersects zi is non-empty for all I in the index set. And if B intersect zj is non-empty, all right, such a j must exist since B is non-empty, right? Where we assumed A and B are non-empty, right? And W is formed by the union of the zi's. So certainly there has to be some j in this collection of I, which gives you a non-empty intersection with B. Otherwise, we could say that B is empty, and that would contradict that B is non-empty. Anyway, so what's that give us? Then if we look at the intersection of A with Zj and, sorry, the wind, it's blowing. A with Zj and B with Zj, well, we get Zj. And yet, the intersection of A with Zj and B with Zj must be empty because that's a subset of A and that's a subset of B, and A and B intersect in the empty set. So we obviously can't have, well, let me see. Let's go on here. Nothing's obvious yet. That's a union, and that's an intersection, right? But this means then that, what does this mean? This means that we've taken the space Zj and we've written it as the union of this set and this set, which are disjoint, which is meaning that we've separated Zj. But Zj was connected, right, by assumption, and consequently that's a contradiction. All right. Therefore, as we've assumed that W was not connected and found a contradiction, it then follows that W is in fact connected. All right. So there's that. All right, moving on here. Corollary. Let A and B be connected. Let A and B be connected. If A intersect B is non-empty, then A union B is connected. Aha! Well, there's the corollary to the path connected thing I was talking about. So this is literally just, the lemma above in the case of, two sets. So it really is straight up a corollary to the lemma. Lemma number 3, I guess. Let x naught be an element of x. Denote C of x naught to be the connected component. Well, I'm not sure it's a connected component, but the claim is that this is going to be the connected component. Cx naught, union of all y, such that y contain x naught, and they're subset of the topological space we're working in X, and Y is connected. So basically, Cx naught, it's the union of all connected sets which contain X naught. All right, and then I've lost my sub naught. That's not good. Sorry, pun partially intended. There you go. Cx sub naught is a connected component of X that is well, I said it is a connected component of X that contains X naught. I mean, I think that actually you can argue uniqueness from this, but anyway, here we go. So observe that X naught, the singleton, just containing one point, is connected, which means that X naught's an element of the connected component. I need a name for this. C of X naught. That will be my name for now. I will stop poisoning the, claiming what I'm trying to prove. Okay. So X is an element of C of X naught. Apply the lemma above to the collection, the family, Y connected that contain X naught, right? And then that gives us that it's connected, right? But also, if A, a subset of X, is connected and it contains C of X naught, then notice that X naught is an element of A, and hence A is, I say, a subset of C naught by definition? Right, A is a subset of C naught by definition. You could say that A is an element of this setup here, I guess, also. Man, every so often there's an ambulance that goes through in that road, and the sound just comes right in here. I don't know what it is. I'd make these videos in my cellar, but there's kind of spiders down there, and they're not bad spiders, but they just make me itchy. So anyway, and my room is full of boxes at the moment, and the lighting's substandard, so here I am outside. Because, hey, fall weather's pretty nice. But anyway, I may have to rethink this strategy in the spring. Because the spring semester is not the spring semester in Virginia. The spring semester is the winter semester in Virginia, mind you. But anyway, so yeah, we've just proved that it's that the C of X naught's connected, and it's maximal, right? Because we assume if we had another connected set which contains it, then it's a subset of it. Anyway, which is to say that C of X naught is equal to A. So there you go. That's the C of x naught. We should just label it the connected component containing x naught. And as such, here we go. Oh, here's the definition I was looking for. So, sorry, that's kind of wired in my systems. That's why you found me saying that when we were doing that proof just a second ago, because it's hard to unlearn. So C of x naught is the union of all connected sets containing x naught. That's the connected component of x containing x naught. So that's, you know, a little bit different. At the start, we weren't talking about a point, right? We were just talking about a subset of the topological space being a connected component, but now we're talking about, you know, a pointed set, a set with a point here. Every topological space is the union of its connected components, and each connected component is closed, and any point is contained in a unique component. Well, no wonder I thought each connected component was closed. It's because I remember the end of the lecture at the beginning, which in retrospect makes that first lemma kind of silly, doesn't it? You know? So, like, if every connected component is closed, that means y is equal to y bar here, you know? Well, I guess it doesn't mean that, because we didn't assume that y was a connected subspace. You know, these ambulances are being very, very disrespectful of my lecture, I'll tell you that right now. The nerve of people. Alright. Sometimes I really, really wish this camera had a pause on it. Sadly, it does not. Okay, so here's the theorem. Here's the proof. Since x is an element of Cx for all x, we can take the union of all connected components of, you know, x, and that's going to give us back x again, right? So certainly, if we take the union of all the connected components, you know, based at a point, we definitely get the whole space. And if we have x naught as an element of two connected sets, right, where they're both connected components, then x naught is an element of the union, right? And let me scooch this up a bit here. So yeah, x naught is an element of the of C, which is a subset of the union. And why not? What do you mean why not? What's this? This is nonsense. Why not? Come on. Sorry about that, guys. X naught is an element of D as well, right? And D is a subset of the union. And also, C union D is connected by the lemma. Thus, it must be that C, I mean, we have C as a subset of this, and D as a subset of this, which means that well, and C union D is connected by the lemma. Therefore, C is equal to C union D is equal to D. Oh man, something's slipping past me here, guys. Why do we get equality here? I mean, that's just set theory that C is a subset of the union, and that D is a subset of that union. And I mean, I just can't remember. Sorry, guys. So we just proved that the union of all subsets which contain x naught is the connected component. So let's see here, union of all sets which, so let's see here. I guess the only thing if they're both connected components, how do I know that there's not something beyond C union D? Let's see that again. Sorry, guys. C of x naught is a connected component of x that contains x naught. It's formed by the union of all connected subsets containing x naught. Alright. And so I mean, I guess C has to be a subset of C of x naught. D has to be a subset of C of x naught, right? Let me say that. Sorry, guys. I mean, from the lemma on the previous page, we definitely have that, you know, C is a subset of C of x naught, right? And D is a subset of C of x naught. And so, and in the end, yeah, I mean, if we take the union of two connected sets, it's connected again. That's true. I'm sorry, I'm not quite seeing why it is that we get that the union has to be equal to the C and D again. Boy, I'm sorry, guys. I'm just dense today. Not in the topological sense either. Anyway, so also C is a connected component, which means that the closure of C is connected with, of course, C is always a subset of its closure. Thus, C is equal to C bar, right? Which shows that C is closed. So I have to get these things, we have to apply lemmas 1 and 2. I'm sorry, guys. I got some kind of mental block here. I think the proof is right in front of us. I mean, so I'm mostly just following Minetti here, not surprised, you know, as I usually do. Just to let you know where and any errors here, I'm sure are mine, not his. But this is section 4.2, unconnected components, and I'm just kind of working my way through here. And you know, basically we're on page 70. If you're keeping score. All right, so in general, the connected components are not open, but sometimes they are. So it's okay. So if every point in a topological space has a connected neighborhood, then the connected components of X are open. All right. So let C be a subset of X be a connected component of X. Suppose X naught's in C with U a connected neighborhood of X naught. Then since X naught is an element of the intersection of C and the neighborhood, and the union of C and the neighborhood is connected by our lemma, then C union U is a subset of C, which means that U is a subset of C, which means that C is a neighborhood of X. So let's see here. Neighborhood of X naught. Every neighborhood in the topological space X has a connected neighborhood, then the connected subsets, connected components of X are open. So to show something's open, if you can find an arbitrary point, right, and prove that there exists an open set around that point, then that suffices to prove that that set is open. And I believe that is what has just happened here. So let's move along. All right, so remark, if f from x to y, all right, is a homeomorphism, then f is both open and closed as a map, right? Because the reason I say that is because if it's a homeomorphism, that means its inverse mapping exists for one thing and is continuous for another, right? But continuity of the inverse map means that the inverse image of an open set is open, the inverse image, yes, the inverse image under the inverse map of an open set is open, and the inverse image of a closed set under the inverse map is closed. But that is tantamount, since the inverse of the inverse is the function again, that means that the function is an open and closed map. So anyway, if it's a homeomorphism, f is both open and closed as a map, and consequently f maps connected components to connected components. This seems like a good homework question, yeah. And if x and y have a different number of connected components, then they're not homeomorphic. All right, so like that's super useful in terms of proving two topological spaces are not homeomorphic, because it's sometimes relatively easy to prove something about the number of connected components, you know? Or maybe you can just see it, like this example here. So if you take the real line, delete 0, and you take the real line and delete 0 and 1, these are not homeomorphic, since on the one hand x is the union of minus infinity to 0 and 0 to infinity, whereas y is the union of these three disjoint open sets, right? So I've decomposed x and y into their connected components, and as you can see, this has got two connected components, and this has got three connected components. Therefore, x and y are not homeomorphic. Another important example, which I think we have like a whole lecture devoted to these kinds of things, so I'm looking forward to that one. Not quite there yet, but I'm getting there. I think it's like at the end of this chapter, actually. So GLN R is the general linear group of n by n invertible matrices. So n by n matrices with determinant non-zero is one way you can characterize that. And you can break that into two pieces, GL plus and GL minus. GL plus being those with determinant positive, GL minus being those with determinant negative. Right? There are no determinant zero matrices in there because those are the singular matrices. And the determinant map, well, what is that? Well, the determinant map is polynomial in the coordinates of the n by n matrices, right? Here's the formula. Determinant of A is equal to the sum of the Levi-Civita symbol contracted across the components of the matrix, right? So this is polynomial. It's an nth order, you know, n squared variate polynomial or whatever. I mean, it's polynomial in the entries of the matrix, which means it's continuous. It's a continuous mapping from n by n matrices to the reals. And furthermore, the reals with 0 deleted, well, that's the range of the determinant. So if we restrict the determinant map to GLN R, then its range is this. And the restriction of a continuous map is, again, continuous. And so, in fact, the image under the determinant of the n by n matrices is the space X from example 2. You know, it's the reals with the origin deleted. And minus infinity 0 and 0 to infinity are connected components, right? And the inverse image of, let me see if you can see it. Let me scooch this up a bit here. The inverse image under the determinant of the negative numbers is GL minus. The inverse image of the positive numbers under the inverse image of the determinant of the positive numbers is GL plus. And therefore, GL plus and GL minus are the connected components of GLNR. Well, I wouldn't say that that's a consequence of the remark, but let's see here. Well, we had a theorem, right, back in the connected lecture that the, I believe, if I remember correctly, the connected image of a continuous image of a connected set is connected, right? So I have, it's been a minute since I thought through that section. Let me just double check here. Make sure I'm not making stuff up. I don't think I am. Come on. Yeah, here it is. Theorem 4.7, right? Let f from x to y be continuous map, then x connected implies f of x is connected, right? So if we take theorem 4.7 and we apply it to my example 3 here, well, it proves that the, I mean, clearly GL plus and GL minus are respectively the images of the positive and the negative numbers under the determinant map. And, I mean, inverse image, I should say. They're the inverse image. Rats. But I had the forward image there, didn't I? Huh. Well, I know that the claims I make here are true. I'm not sure I have quite proved them yet, though. I mean, certainly GL plus and GL minus are disjoint. You know, you intersect these, they're definitely disjoint, right? And it's also fairly clear that they're maximal because, like, you can't take a subset of matrices that is bigger than GL plus inside here without, you know, getting into here. So I think that you can make an argument like that implying maximality of these sets. And since they're connected, and I guess that's the question, is how do I know these are connected? So they're the inverse image under the determinant map of a connected set. Sorry, I feel like I'm forgetting. I think I'm forgetting things we've already done in the previous lecture at this point. I'm sorry if this is the bad thing when I take too much time between when I write these notes and when I talk through them. I start doubting what we know. Well, we know that the inverse image of every fiber is connected. Well, that's not what I should say. Yeah. We have a theorem about inverse images of fibers there. Wheel. Huh. Well, guys, I'm not sure what to say right here, right now. I'll have to think on it, and maybe I can return to it in the next lecture. All right, guys. So, thanks.